Hello everyone, how are you? Welcome to our webinar of hydrogeological modeling. This is the first webinar that modeling that we give in English, and I hope that you can enjoy Geomodelr and how to make much easier to create an hydrogeological model, a conceptual model that can be used in numerical tools like Modflow and Model Muse. Let's wait a few seconds for a few more people to get in. I'm also going to give you in the chat a link to enter to the webinar and to chat with us directly. If you prefer, or if you prefer, you can still watch it from YouTube. Can still watch it from YouTube. So let me introduce you to my companion here. Hello everyone. Hello everyone. So I'm Ricardo and this is Daniel. I am the creator of Geomodelr, and I am going to be the main presenter here. Daniel is our technical leader, and he also developed all the module that connects Geomodelr to Modflow. So I'm going. Give me a second, and I'm going to give you the link if you want to interact directly with us, and then we'll get started. Okay. Okay, so I'm going to share you my screen right now. Great. So let's get to the point. So what are we going to do? We are going to create an hydrogeological conceptual model. An hydrogeological conceptual model represents, in a simplified way, the hydrogeological characteristics of a specific area. It takes into account lithological properties of different formations and geological units. In this case, we will model a swamp. We will call it Ciénaga from time to time, which is a Spanish name. It is modeled after it is a model from northern Colombia, and this is one of Geomodelr visualizations. This is the visualization of the map and the cross sections. So we can see here in the map that we have three units. You can click on it. You can move it around. Let's hide it to see the different cross sections that we can see here. So here at the top, we have conglomerate arenisks, conglomerate sandstone. We have the next unit is conglomerate. It's sandstones and conglomerates. The final unit is sandstones, and finally below it, it's again conglomerate sandstones. This unit here, it's a high conductivity alluvial. This is our geological model, and we will be seeing how this model becomes 3D and try it out. So let's get to what's a hydrogeological conceptual model. So the hydrogeological conceptual model it's composed of the geology, which is regional and local. The geology has lithological units, structural geology, general, and from this we get the general flow directions and also the hydrogeological units. We need also the physical environment. We need a digital elevation model, the surface cover, the slopes map, the flow direction, and also the hydroclimatology, which gives us precipitations, runoff, temperature, evapotranspirations, and soil humidity. With these two, with the physical environment and the hydroclimatology, we will create recharge maps. And from this, we will have the zones of groundwater potential. This is a conceptual model. We can create this conceptual model in Geomodelr, but we will also see how this conceptual model gets to a numerical model also in Modflow and Model Muse using our model developed in Geomodelr. So these hydrogeological units are units that have similar hydrogeological properties. So we here see the three main hydrogeological units. The first hydrogeological unit is this, the alluvial. We can see that there is a very, 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 very thin layer here, very thin layer, and this is associated to the deposits of alluvial, which occupy mainly of the east area. This unit has very high potential to store and condense water, mainly because the kinds of sediments, gravel, and sands producing high porosity. Okay, so we have the the other hydrogeological unit is the swamp, ciénaga. The swamp is, as you can see here, is most of the geological model. We can see here that this unit has a constant exchange of flow with the alluvial unit. We can see the space left by the alluvial here, by the alluvial here. We can see also that this unit is composed of three hydrogeological units. It's these hydrogeological units. We will see them more clearly. As I said, this is the conglomerate sandstones. Is this brown? There is also the sandstones and conglomerates, which is below this, and finally sandstone. And below those also conglomerate sandstones. Finally, we have a unit that is not modeled in 3D here. Why don't we have it modeled in 3D here? Well, because we are going to use this unit as we are going to use as this map, or more like this whole unit as an input in Model Muse to show that we can still modify some things after we export our geological model from Geomodelr. Okay, so let's get to the final. Finally, we need to have some properties. As we said, we divided the units in three according to its aquifer potential. So we have the hydrogeological unit 1 with a very high aquifer potential. We have the hydrogeologic unit 2 with a medium aquifer potential. And we have the hydrogeologic unit 3 with a very low aquifer potential. And we test, and by testing the different units, we can have finally their hydraulic properties. So we have here the horizontal conductivity, and we have also the vertical conductivity. And we see that the conductivity of the first unit is very high. It's 3 meters per day. And we see that the vertical conductivity is 0.3. This is it's usually done by hydrogeologists to obtain the hydraulic conductivity in the vertical direction, is to make it a tenth of the hydraulic conductivity in the horizontal direction. So we also see it here. We see in these conglomeratic sandstones, we see that the hydraulic conductivity is 0.07. In sandstones and conglomerates, we see that the hydraulic conductivity is 0.05. Yeah. Hi, Salvador. Yes, the presentation will be online after the webinar. We will send you the recording of the webinar and everything else in it. As I said, I have posted in the chat a link directly to this webinar, so you can connect directly with us, and we can answer your questions live if you want to. Great, thank you. So finally, sandstones have another hydraulic conductivity. Finally, we have the geometry. This is a representation of the cross sections. This is a cross sections model in Geomodelr, and this is the 3D model as it is full with all the units. Yep. So we here have the alluvial unit. So we turn it off here. Yep. We have the sandstone unit. We just turned it off. It was the white unit. We have the sandstone and conglomerates here, and we finally have the conglomeratic sandstones. Okay, so these are our 3 units modeled in 3D, and we will see how to model them in a few seconds. But before that, I want to ask you some questions. If you want to answer, you can answer in the YouTube chat, or you can come here and answer it directly. So, what's your experience with hydrogeological modeling? Do you have previous experience with hydrogeological modeling, and what software have you been using to make hydrogeological modeling? Okay, as I say, you can always you can enter to the Hangout link. If you're having some problem entering there, then you can tell us. Also, okay, so let's continue with what we came for. We came for modeling in Geomodelr. So from here, let's go to our page of models. So what we can see here is what we would see if we had well, you all have an account in Geomodelr because you have to create an account to subscribe to these webinars. We can see here the main page that we see when we log into Geomodelr. To create a model, we just call it swamp model, for example, and we call it swamp. Oh, I'm sorry, I'm not sharing the screen. Okay, here again. Okay, so this is the screen that we will see when we log into Geomodelr. We call it. We can call our model swamp model, and I'm going to just create it. Let's see if it doesn't exist still. Okay, so let's go to swamp model, and we will see here the main page of our study. Okay, you can see here that we haven't set up a geological model. We can see here that the files repository is empty. We haven't uploaded any file. We can see here all the pages that we can go to. We have the file separation. We have the articles page. That is what we were seeing before. We were seeing an article modeled in Geomodelr, and we can also see how to export our model, which is a page that we are going to use in a few moments to export our model to Modflow. We also can set up the permissions of the study. We can give permissions to collaborate, to contribute, to review, or to view to our different users. Okay, so we don't need this study. We already have a study that we can work in. So let's delete this swamp model, and let's go to our Ciénaga model. Okay, so this is Ciénaga. This is our actual study. This is the actual study where we will that we were working at. Okay, so here we have the different files that we will use to model our hydrogeological model. So we have here the different files that Geomodelr can accept. One of those files are shapefiles from ArcGIS. They have to be georeferenced. You can zip them all and you can upload them here. You can also see, for example, GeoTIFF. GeoTIFF is useful for several things. One of those things is to allow us to have a topography. So we can use a GeoTIFF, and we can use it to show, well, as an input to the topography. Okay, we will see why it's important in a few seconds. And we can also see several profiles made so we could digitize them and use them in Geomodelr to make our geological model. Okay, so here we have the units manager. We have several things. I'm going to make something that that you probably don't want to do too often, which is to delete our model. We're going to delete it because we're going to create one from scratch, so you can work on it. Okay, delete our model. Great. So Selvazul asks, how do you deal with water table levels which are very near to the surface, 1 meter to 5 meters? Well, in this webinar, we don't have a piezometric values to fit again the geological model. To fit the geological model in something like PEST. But in next webinars, we will show it how to do it. In any case, this is done in Model Muse. This is not done in Geomodelr. In Geomodelr, what we are going to build is the conceptual geological model, the conceptual geological model. So, well, I hope we have answered to you. Okay, so here we have to set up our geological model, and the first thing we need is digital elevation model. So something we can do if we don't have anything else is to download one from the Shuttle Radar Topography mission. You just have to say next if you want. but we have one digital elevation model here, so we're going to use it. It has to be in geotip. I'm going to say next. Next, we need a geological map. Of course, we can create the map from scratch. We can draw it from zero, but we already have a geological map, so we are going to use this geological map. You can see in this geological map that it has lithology, caliph, unit. We're going to select unit as the name of our unit. Units are very important because it's what Geomodelr does interpolate units and faults, but here we don't have any faults. So next we're going to load the rest of the properties to see them when we want. And we don't have faults here. This is not a faulted model, but we will show you a faulted model in a bit. Okay. So let's click next. And Geomodelr makes these inferred values. Okay. So so it gets the coordinate system of the map, the coordinate system of the topography, first the coordinate system of the map, second the coordinate system of the topography, and then this is what it's showing us here. This was the coordinate system of the geological map. And here it's the intersection between topography and geological map. And we have that this is going to be our modeled area, but we can georeference it manually. You can search for a coordinate system. We have supported several thousand coordinate systems. So we can, for example, look for Minnesota. For Minnesota, and we can see or for example Canada. Okay, so we can see here several coordinate systems that are used in, for example, Canada. We can narrow it down to search for coordinate systems, or if we really don't like this search box, we can also use epsg.io to search for a coordinate system in EPSG code, and we will receive that coordinate system EPSG code here. Okay, we can also enter the bounding box here. We can, for example, enter this bounding box by clicking on one side and clicking on other, but we can also modify it from here. Okay, so so we can do all that, but we don't need it here, so we will leave the inferred values, and we will create our geological model finally, and let's do it. It will take a few seconds. Thanks to you, Selva Azul. It will take a few seconds, so don't be shy. If you want to come to the chat and interact with us, we would really appreciate it. We're going to give you again the link for those of you who want to enter. If you're having any problem, just tell us. Okay. Okay. Sorry, I entered to the wrong page. Okay, so we have here our geological model that we just loaded. This has some dummy colors. We are going to see the map, the geological map of that we just used. So here we have our geological map, and we have some operations on top. But we have three kinds of operations, which are unit operations. Unit operations are for changing units. Fault operations are, as its name says, to create faults. And node operations, these are to help us with the other operations. Okay, So let's see unit operations first. Unit operations are the simplest thing in the world because the only thing that you have to do is you have only two operations to separate a polygon, one polygon, convert it in two, and to join two polygons, convert them into one. So I'm going to separate the polygon here by clicking in one node in one side and going to the other. I can take a deviation and select, for example, a polygon in the middle, and I can keep going, but I need to keep going until I go to the other side of the model of the unit and can finally split it. When I split it, the color of the nodes that I was creating changes to red. You can see, for example, what you need to do if you are unsure of what you are doing and what you need to do. You can go down here, and when you do something, it will tell you what you can do. You can, for example, grow this arc, go here, and it says, well, you haven't finished. You can need to create a new arc, and finally divide the unit in two. The other operation is to join units. And to join units, it's simpler still. We can, for example, select one unit and select another unit, and there you go. You have joined two units, and you still have a solid map, a map with a good topology, and you have edited really quickly. The other kinds of operations are fault operations. We don't have faults in this model, but we can have faults, and they are going to be beautiful. Okay, let's finish this. Okay. Okay, so to create a fault, what you need to do is to start a fault in some point and to follow creating nodes until you're done. And when you are done with the fault, you can finally click in the last point. You can extend those faults by clicking in one of its sides. Finally clicking. You can also separate faults so that you can treat the two faults separately. For example, if you want to give a name to one fault, or if you want to eliminate one fault and not the other. Okay, we can give, of course, we can give name, and we can select properties. Names are like units to fault because they are the thing that we are going to interpolate, and we are going to show it in a few seconds how interpolation and how everything else works. Okay, so we also have node operations. Node operations work to help us with the other operations. For example, if we don't want to divide the polygon here in one of the points that we have, we can create a new point, a new node, sorry, and we can divide it. There. Can also remove, move nodes to a new location. We can join a fault node with a polygon node. We can also separate them. This is the inverse operation of the previous. We can also remove nodes to make things sharper. Finally, we have the options. The options will help us to draw. Of course, we have we can hide the nodes when we want. We can show the object's information. We can set a reference point, for example. Oh, sorry. We can set a reference point. We can also set the background image layer. We can load here layers, and we can also add more layers here. we are, for example, going to add a layer of pliegues, which is faults. We're going to load the type, going to say submit. Submit, we need a name for it, so it's faults. I'm going to say close. Okay, let's check the faults, and you can see here the different faults that we have in our geological map. We are going to go back to the main page, and we're going to abandon this. Okay, so we also have now enabled the visualizations page. The visualizations page will show us our model in 3 dimensions. And at this point, we don't have any cross-section. We will only see the topography, and we will only see the different units. So let's exaggerate the units. For example, we can exaggerate them separately. We can exaggerate them above and below the sea level. We can also do this in cross-sections. We will see it in a few seconds. And let's get here to create cross-sections. So how does Geomodelr work? Geomodelr works by interpolating cross-sections. So I'm going to come here. I'm going to add a vector layer, which is here, which is called profiles, which is profiles. I'm going to call it or cross-sections, rather. I'm going to call it cross-sections. I'm going to say to put the name on it, and I'm going to close. Okay, I didn't show it. So let's show the cross-sections. These are the different cross-sections that we were given. And we can digitize them. So let's go and let's work in the cross-section that in one of the cross-sections that we have here. For example, this cross-section is called AA. So let's select our first. Let's create our first cross-section. This cross-section is important. It's actually very important. This cross-section is the cross-section that will tell us how our geological units will interpolate. Because we will have a direction in which units are supposed to be interpolating. So let's select, for example, this perfil B. Okay, let's go from here to here, and all our cross sections that are part of the interpolation will have to be parallel to this one. Okay, let's also say a key here -1000 to say this is the bottom of the cross section. This is the bottom coordinate of the cross section, and let's give it a name. It was called BB there, and we are going to call it BB here. Finally, click submit. Okay, it will take a few seconds. And when it's finished, we can click on it. We will see the cross section here. Okay. We actually don't like very much the colors of the unit, so we're going to change these colors. We can click on, for example, UH1, and we can open for example, the cross-stratigraphic chart. So we can select the color that actually is, or we can also click here to select it from a color, from a random color that we want. We can say, for example, that this is lower, and we're going to say change color. We can see here that it changed here, here, here. Okay, so we're going to start by dividing this cross section. If we want to divide it to the other side, we can add nodes here. Okay, let's go. We can do this, for example. We can also do this. I'm not doing anything meaningful at the moment. I'm sorry, but we need to move faster during this webinar. But I'm going to give it unit names. Okay, so I'm going to select this as Hydrogeological Unit 1. I'm going to select this as node classification. I'm going to select this as Hydrogeological Unit 2. I'm going to select this as Hydrogeological Unit 1. Of course, you can see this is not real, but let's going to use it. Let's use it. Okay. Okay, so we have this cross section here, and we can create a new cross section. We are going to see that the new cross section that we are going to create is going to have to be parallel to this if we want to interpolate it. But of course, we can select not to be part of the interpolation. We can use the interpolation to find the value here, but it will not be part of the interpolation. If you want it to be part of the interpolation, we select that it has to be part of the interpolation and that this has to be parallel. And we're going to call this another cross section CC. Okay. And again, we're going to say it's at under 1000. And we're going to say, let's interpolate a geology. And we're going to say, okay. And it's going to make pretty much a copy of what we did. Okay, it's not going to be anything special right now, but we can modify. But the point is, we can modify it really quickly, and we can modify it really fast with the tools we have. For example, we want here to join these two polygons, which didn't join in the previous cross section, but they are joined here. And let's go into save it, and let's go into Senegal. So what Geomodelr guarantees is that the cross sections you create will be part of the model anywhere, and also that it will create an interpolation, a very smooth interpolation that will give us as a result something really smooth, something really nice. So let's create this cross section in the middle, and let's go here. Let's say click to interpolate, and let's say submit. Okay. So what we are going to be seeing here is how this cross section is moving between this to this. Okay, and we can see it here more thoroughly in the visualizations page. You can see it here. Okay, so we are going to create a visualization of a 3D geological unit of this unit that we have here, of course. And this unit we have here, we're going to say it's an unbounded surface. We don't need it to be bounded. We don't need it to be bounded right now. And we are going to say it's going to be HGU1. And we're going to say submit. It's going to process for a few seconds. And it's going to be ready. So we can see here how our unit was formed. It looks actually really cool, but it will look a bit cooler when we combine it with the cross sections. Okay, So we created this combination. Of course, the map doesn't have to do anything with it, but we can see here how Geomodelr is capable of creating this geological model that changes from section to section, and it will create those units that pass. Actually, they are pretty exact, exactly from there. The interpolation algorithm of Geomodelr guarantees this, so that you don't really have to. Well, what you have to do is to create more cross sections and to interpret, and then you will have a 3D geological model, which is going to be really easily used. Okay. So of course this model, well, it's pretty ugly. We didn't use any information that we need. So well, I'm going to show you something else here. I'm going to show you, for example, how to see background image. Okay, so we here have a profile that was interpreted by someone, and he sent it to us, and we can see here how to see it in transparency and how to digitize it in our platform Geomodelr. That's what we did to create our geological model. Of course, to be able to digitize an image, to be able to have it as layer, you have to georeference. Here we have the repository. We enter to the repository, and these are some operations that we can use. From here, a very useful operations are to georeference an image. We can select it. We can, for example, select the profile. We can select one point and give it a coordinate x, y, z. A second point and give it a coordinate x, y, z. Third, a fourth, and we finish giving it coordinates. We can say submit. With 4 coordinates, we can georeference anything, but we can also we can select more points if we want, and it will only make it better. Okay, so let's go here again. Let's delete this model, and finally let's use a version that we have saved and set it as model. Okay, it will take a few seconds to save, to set, and meanwhile I'll show you this. This is how we create a version. We put a name here and we say submit. Okay, so this is how we create a 3D geological model. We have in visualizations. This is in the list right now. It was of the previous one, so we can click here in visualizations page. Okay, so we can see in visualizations several visualizations that we have available. For example, we can create a block diagram. This is a really, really nice and cool visualization of this model. And we have to say which is the bottom coordinate. I'm going to put -500, -500. I'm going to put the top coordinate at 300. And I'm going to say submit. Block. Okay. Okay, so here we have a block model of our geological model. That is what we are going to interpret in a few seconds. We can also create units. We can also create bolts. We don't have bolts here, but I'm going to show it how some nice bolts we'll get in a few minutes too. We can combine them to have all the information together. We can also plot boreholes. Boreholes are one kind of file that is not here. Boreholes and structural data can be uploaded as a zip file. There are zip files in our tutorials that you can use as an example. Okay, but it's basically color survey color survey interval. They are pretty standard files that you will find pretty much anywhere. Okay. Okay. So let's continue then to Daniel. Daniel is going to show us how to model, how to take this model that we just created, this solid model that we just created, because in Geomodelr everything is always solid from the first cross section. And Daniel, after this, is going to show us how to use this geological model into Modflow to simulate groundwater flow. So I'm going to give you the introduction to Daniel. Give him an applause, and let's get him to help us. Okay.
Okay, hello everyone. Let me close this window, please. I'm going to delete some files. This one and this one is. Okay, everyone. Okay, then when we finish the creating the entire model, we go to the main page of our study, and on the right side we can see the export page button. Then we click on it. Then the export page appears. In this part, we have all the units that were created during the entire study. In this work, we are going to use only four units: the sandstones, conglomeratic sandstones. This is the sandstones and conglomerates and the alluvial deposit. If you want to delete the other units, you can go to the main page. Let's go to the main page. This is the main page of our study. And you can select the Open Units Manager and delete the units that you want to delete. But in this case, we're not going to delete any unit because the algorithm ignores the units that are not used. There, this is the export page, and you need the information that you need of all units is the hydraulic conductivity. Firstly, we're going to write the hydraulic conductivity, the horizontal hydraulic conductivity for this unit. The value is 0. Give me one moment. 0.04 meters per day. The length, the length unit corresponds to meters in the model, and the time units correspond to days. By the algorithm export the information that it export use the second time unit, but we can change this value using Model Muse. Then we're going to write here 0.04. This corresponds to the horizontal anisotropy. This value is equal to the rate between the conductivity in the y direction and the conductivity in the x direction. For example, if the conductivity in the y direction is twice of the conductivity in the x direction, we pick 2, or if this value is equal to 3, if the conductivity in the y direction is 3 times of the conductivity in the x direction, and so on. We're going to put just 1 on the vertical conductivity. In several works, if you don't have the information about this parameter, you can assume a value equal to the 10% of the horizontal conductivity. And then we are going to write 0.004. This is the conglomeratic sandstones, and the horizontal conductivity is 0.07. Horizontal anisotropy is equal to 1, and the vertical is 0.007. This unit is not used, then you can put any value that you want. For example, 1, 1, and 1. This unit corresponds to the sandstones and the conglomerates. Then we're going to put one moment.
Okay, just 1 second. Okay, we have to. Yeah. Oh, Alfredex, thank you for connecting. Thank you for connecting to the webinar. Do you want to tell us to ask us a question? Okay, Alfredex, when you're ready, you can tell us that you need to ask a question. Right now, we're going to mute you, but you can unmute yourself when you need it to, Okay. And I'm going to give again the presentation parts to Daniel. Okay.
Okay, then here we have the sandstones and conglomerates, and we are going to put a value equal to 0.05, anisotropy, for example, equal to horizontal anisotropy equal to 2, and a vertical conductivity equal to 0.005. But we are going to inactivate this unit because, for example, when you have clays or units that have a low value, a very small value of horizontal conductivity, hydraulic conductivity, you can inactivate this kind of units. And the last one is the alluvial deposit. The value is equal to 3, horizontal anisotropy equal to 1, and the vertical conductivity is equal to 0.3. These units are not used in the model, then we are going to put any value, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1. Okay, then we have two options of algorithm, the simple grid algorithm and the adaptive grid algorithm. Firstly, I'm going to show you how the simple grid algorithm works, and after that I'm going to show you how the adaptive grid works. Then here we put the number of rows that we want in our model. For example, we are going to put 50 rows, 35 columns, and 30 layers. These layers, the algorithm uses the layers to discretize the z direction of the model, and the layers do not correspond to each unit. Then the last, we are going to put the name of our exportation file. I'm going to put simple webinar, and we are going to submit the information. Then we have to wait a few seconds.
Okay, so Meanwhile, while we wait a few seconds, I want to ask you some questions about what you have seen here, and what's your experience with Model Muse and Modflow? Do you guys have much experience with Model Muse and Modflow? Do you have experience only with Modflow but with other processors? Or do you have experience of you don't or you are new to groundwater modeling with Modflow? If you Fredex, do you have any question? Okay. It's okay. You can ask questions at the end of the conversation, but we want to tell to you that Geomodelr exports Modflow files directly. So these Modflow files can be read by pretty much any preprocessor. So we are going to use Model Muse because it's free, because it's available, because you can use it right now at home. But we have tested Geomodelr outputs as in Visual Modflow, for example, in PM, Win, and in other preprocessors. So if you have another preprocessor of preference, you can always use it. Okay. So so the export should have finished. Okay.
Okay, we are going to continue. Then here we have the file that we need to use in Model Muse. We download the file right here, and we go to the download folder. I'm going to put it in my work folder, Geomodelr, right here. We unzip this file. Okay. And this is the folder that we have download from Geomodelr. And this is the most important file that we're going to use. The first one is the VAS file, and this file has information about which units are active or inactive. The DIS file has information of the geometry of the model. The LPF file has information of the hydraulic conductivity, and the NAM file or MAM file has connects these three files. Then we're going to open Model Muse. I have to wait a few seconds.
Okay.
Then we select the import Modflow 2005. We click on it next, and we need the information of the origin, the coordinates of the origin. The origin of our model is located on the upper left corner, and we can see this information in the main page of the study right here. Then the x origin corresponds to this value. Sorry.
Okay. So from okay. Okay. So we are sorry we didn't share the screen during a few minutes.
And I'm going to.
But
to close this window. Sorry. Then.
Okay. we we are really sorry for the inconvenience that just happened. But we're going to show how to download. What we were doing was that we were creating our file to download and to use in Modflow and Model Muse, and we're opening it. So we didn't share the screen, but now we are sharing it, and we have downloaded the file. We have unzipped it, and now here we're going to open again the file so you can see how Model Muse works with these files and how we can from Geomodelr upload conceptual geological model with all its geometry inside, with all its geometry defined. Okay, so I leave you again with Daniel.
Okay, then this is the more important file so that we export. Then this is the BAS file. This file has information about which units are active or inactive. The AS file has information of the geometry of the model. The LPF file has the information of the hydraulic conductivity, and the NAM file, the last file, connects these three files. Then we have to open Model Muse. We select import Modflow 2005, and we need information of the origin of our model. The origin of our model is located in the upper left corner of the geometry, and we can see this information, the X and Y coordinates of the origin, and the main page of the study right here. Then the X origin corresponds to this value, the Y origin corresponds to this value, and we have to open our file. This is our folder, simple webinar, and we select the simple webinar, exactly the NaN file. We select OK. Then we have to wait a few seconds. Anyone has questions?
Yep. Modflow might take a few seconds. You can create public geological studies for free. You have seen it. This feature of exporting to Modflow and some export that we will do in the future are going to be features only of private studies. But if you have something interesting, or if you that you would like to tell us, or if you want to test our hydraulic our export to Modflow tools, you can just send a mail to support@geomodelr.com, or you can use the chat in the app, and we will answer to all your requests. So thank you very much.
Okay, then you can see Model Muse. You can see right here that the simple algorithm use or create a regular width of the model. Let's plot the hydraulic conductivity in the X direction to see all the units. We show this value, transform, and apply. We're going to compare it with the visualization in Geomodelr. Okay. For example, we can see right here, this is the topography of our model, and you can see right here the model, the units that are using in Modflow. If you want, a more accurate grid to in this kind using this algorithm, you have to use high values of rows and columns and layers if you want to see a more accurate grid of the model. Then let me show you the object the Model Muse import. This is the object, and we're going to open it. Then imported data, and this all the information that we have. This is the model top. This is the value of the topography. Remember, we were using 50 rows and 35 columns. Then is equal to 1,750 cells per layer. Then we have the information of the layer 1, layer 2, layer 3, and so on. We have the information of which cells are active or inactive. We have the information of the hydraulic conductivity in the x direction. We have the information of the anisotropy, the horizontal anisotropy, and the information of the vertical hydraulic conductivity. Right here in dataset, Model Muse is using the information of the topography of the geometry. Here it's importing the model top. Here it's using the value of the layer 1. This is correspond to this value, and so on. Let me close this window. I'm going to hide this object and data, the data set. And here in active, there Model Muse is importing the information of the which cells, or yeah, exactly which cells are active or inactive. Here is importing the horizontal anisotropy, the hydraulic conductivity in the x direction, and the hydraulic conductivity in the z direction, or the vertical conductivity. Then let me show you the inactive cells. We're going to put the show active. If you remember, we set to inactive the unit that correspond to the sandstones and conglomerates, and is equal to this region that we see right here. This is the sandstones and conglomerates. Okay, let me close this window, and I'm going to show you how the adaptive algorithm works. Firstly, we're going to load the information that we used in the last model, and they load, Geomodelr loads all the information. I'm going to change the value to 1, and I'm going to put it active. And I'm going to select adaptive grid. Then, for this example, we're going to use 150 rows, 110 columns, and 30 layers. We have to write these parameters. Minimum layer thickness is equal to then correspond to the minimum distance allowed between layers. For this example, we're going to use 2 meters. The maximum angle is the maximum angle allowed between 2 consecutive points in the same layer. We're going to use 30 degrees. You can use 10, 20, 45 degrees. You can use the combination of parameters like you want. Then we're going to write the name, adaptive webinar. We are going to submit. Okay, the algorithm is running. You have to wait a few seconds, 30 seconds, 45 seconds. It depends of the number of rows and columns and layers that you are using. Okay, it's done. Remove file. I'm going to look for this folder. I'm going to move it to our work folder. Unzip it. Okay. And this folder has the same file that we see in the last folder. And we're going to use open Model Muse. We're going to import information of this folder, the adaptive algorithm. We select import Modflow 2005. The X origin is the same. 1,465,000. And we import adaptive webinar file, and we click on OK. This algorithm works. They try to fit the layer buttons to the shape of the unit. Then we can see a more accurate grid in comparison with the other algorithm. We have to wait a few seconds. It's open. It's loading all the information.
Okay, so we developed this algorithm to look much like what hydrogeologists usually do when they have to create a geological model with Modflow. They follow the layers precisely and then intrude them. But this is pretty much automatically. And we will see in a few seconds when we open this geological model in Model Muse, how it follows perfectly every layer and how it represents perfectly what we have modeled and what we are seeing in Geomodelr. So this is a new way to create geological models and to evaluate them conceptual geological models directly. That involves very little work from your side and gives results that are pretty outstanding. So uh, thank you for coming to our webinar. As we have said earlier, if you have any question, if you have a project that you would like us to see, please just send us an email to support@geomodelr or contact us through the chat. Okay, so I'll leave you with Daniel and his great model.
Okay, then we have our model, and here you can see how the layers fit, to the shape of the boundaries of the units. You can see right here. Let me show you. First, I'm going to plot the value of the kx to show you how this model looks. Then we can see that this all the layers try to fit the boundaries, the geometry or the shape of all the units. Have to wait. You can see right here our model, Geomodelr. You have to wait a few seconds because we have a lot of. If you remember, we are using 150 rows and 110 columns, and then it's a heavy model. You can see it's awesome, this algorithm. Let me show you this. Here you can see the geometry, the layers, and how the layers fit with the boundaries of the unit. And we can see right here a 3D model, a 3D view. You can say is very similar to that of Geomodelr. Right here and right here. This is the topography. You can see this, for example, this cross section. We're going to see the layers, and we can say we can see the same cross section, and we can see this model is very similar. If you remember, we put 30 layers, but in this model we are going to click in model, layer groups, and we see that we have only 16 layers because the algorithm find that the optimal value of layer is 16 in this case. And okay, then we have low layers. It's better. By default, all the layers are convertible. Then we can change, for example, the last layer from convertible to confined layer. We click on OK. The last thing that we're going to do is edit the georeference information right here. Edit georeference. Oh, sorry. If you remember, we put our hydraulic conductivity are using tiny units equal to 2 seconds, but we need to use a tiny unit equal to day. Then we can go to Modflow options, and we can change from seconds to days. Then we click on OK. And the last thing that we have to do is edit. Okay, we are going to change the georeference. We set the start date to today. Today is 14 December 2017, and we have to write the EPSG code. Then we can get this code from the main page of our model. Let's go to the main page, study, Senaga page, and here is the EPSG code. Then we're going to put the same 3116 and OK. Then from this point, we're going to make an example of a simulation using river condition and recharge condition. Firstly, if you remember, Ricardo said that we don't create a unit that corresponds to clays. Visualization page. This unit that we are now using in our model corresponds to clays, and we are going to inactivate this region using an ASCII raster file. Let me show you how. select file, what? Then we are going to inactivate this region using an ASCII file. File, import ASCII file. Then we go right here and we're going to use this file. We select set values of intersected cells and point closest to cell center and OK. Then I'm going to show you how is this file. This is an object that has a value equal to 1 if the cell doesn't correspond to the clays, to the region of the clays, and a value equal to 0 if the cell corresponds to about or belong to the region of the clays. Oh, sorry, it's not the object. Sorry, this is the object. And then we can say this region is equal. This region has a value equal to 1 because these cells do not belong to the clay region, and these cells correspond to the clay region. Then we are going to inactivate this region. We're going to data, edit datasets, active. Then we're going to edit the formula. Then we use the imported file. This is the imported file, ibon clays, and we say ibon clays equal to 1. Then set OK, because we're saying that if this file is equal to 1, then the cell are active, and it's different to 1. The cell is inactive. When we apply, close, where show active. This part, Model Muse is going to show me only the cells that are active, and you can see this. Okay. After that, we're going to change the solver that we're going to use in our example, because I'm going to select the Newton-Raphson algorithm to solve this problem, because I have done several examples. The convergence of the Newton-Raphson for this example is faster than the preconditioned conjugate gradient. We have to wait a few seconds. They are converting all the information to the Newton-Raphson solver.
Has anyone used the Newton-Raphson solver? Has anyone used the preconditioned gradient conjugate solver? What are your experiences using one or the other? If you have to say something, please say it in the chat, or get into our inside into the internal webinar. Okay.
Okay. You can drink a cup of coffee while we are waiting for this algorithm. Okay, then Model Muse say us to it's a good time to activate the OPW flow package, and then this is that are we going to do. Then we click on Model package and programs. Then we're going to flow, and we select the OPW package. This package works is works with the Newton-Raphson solver. And after that, we are going to activate our boundary condition. We have a specific flux. We have our recharge, change to top active cell, and we have a Cauchy. This is a Cauchy condition that depends of the heat, the head, and the flux of the cells, and we're going to activate the river package. Okay, we're going to show the edge of the Arctic zone. We are I'm going to import the ASCII raster file, the rivers. We're going to export the rivers. And okay, right here. Then this object corresponds to an ASCII raster file of the rivers. This is the river. Then we're going to open this object. This object is applied in the topography, and then we need one Z formula using on the model top. This is the topography model top. We want to model feature and activate the river package. The starting time, you can, if you make double click right here, we have the default values of the starting time and the ending time. The river stage corresponds, for this example, it's model top minus 0.5 meters. The conductance, the interpretation is direct, and we set this value equal to 60. The river bottom, for this example, it's model top minus 1 meter. Okay, okay. Then we're going to hide this object. I'm going to export the last boundary condition, the last ASCII raster file, and this file corresponds to the recharge. We click right here and right here, and okay. Then we're going to create a new object to set the recharge condition. Going to boundary condition recharge. This is the name of our object. We don't need a Z formula. Then we put this in 0, model features and recharge package. Double click right here to activate the starting and ending time 0 and 1. This is the value this is the default value. On the recharge rate, we find our file. This is recharge, and okay, and okay. I'm going to show you the plots of this boundary condition. We open right here. We look for the boundary condition, the two boundary conditions. Boundary conditions, Modflow recharge. And this is the recharge condition. Have to wait a few seconds. And this is the recharge and the value of the recharge condition. Then we're going to change to river conductance apply. And we have to see a value of 6 or 60. Sorry, 60. On the rivers, 0 different parts. This is the rivers, if you remember. You can see the value right here in this area. It's equal to 60. If right here, you don't have any value of this boundary condition. Going to turn off all the plots, apply, and we need to change the information of the numerical solver. We're going to Model, Packaging Programs, and we go to the Solvers, and this is the Newton solver. For this example, I have to use 500 iterations, because if we use a lower value like 150 iteration, maybe the algorithm do not converge. Okay, and the other that we have to do is the other thing that we have to is edit data set and define the initial head. When you don't have the experimental piezometric value of on your model, you can set this value equal to the model top if you don't have information about the piezometric or the piezometric values on your model. Then we apply this value, we close, and we're ready to run our model.
Okay, so Selvazul asked previously about how to deal with water table labels, which are very near to the surface. Okay, so Daniel here used as initial heads actually the surface levels. So we numerically it should have no problem. And actually some users told us that they use a mean of the water table levels and subtract them from the surface from the topography. Subtract that mean from the topography to have initial heads, and then they start to calibrate the model with the water table. However, we don't have piezometers here, so we are not going to do this in this webinar. In a future webinar, we're probably going to use that and to calibrate our model. So thank you.
Okay, we are going to run our model, Modflow now NWT, adaptive webinar. I'm going to save this file as webinar example. Save. On this part, in this part, the Model Muse Modflow is this information is, or how can I say that? The information Model Muse converts the information to a linear to solve a linear system. Then you have to wait a few minutes
To do this. Okay, well, we wait for Modflow to do this. So I'm going to recapitulate what we've seen. We have seen a presentation of what's a conceptual hydrogeological model. We have seen how to create that hydrogeological conceptual model using Geomodelr, how to define all the geometries with the solid modeling that Geomodelr produces, which is really easy for geologists to use. And we have used that model directly in Model Muse and Modflow. And right now, we have seen how with the regular algorithm, it exports some regular cells, and with the adaptive algorithm, it tries to do what a professional hydrogeologist would do, but much faster and without wasting so much time, which is to follow all the layers precisely. Okay, and now we are waiting for the results of Model Muse for the groundwater model to finish. After setting up the boundary conditions and after setting up some other conditions directly from Model Muse. Okay, so I leave you with Daniel again.
Okay, everything is okay. The people that work with Model Muse know that we want 3 happy faces, and we have 3 happy faces. Sorry, right here. We close this. We close, and we are going to import the results of our simulation. We open the FHD file, and we click on OK. Then we have to wait again
Seconds.
a few seconds, yeah, at least.
Seconds. It's importing every layer. It is importing every layer, and let's see how it goes.
You can read if you want the second cup of coffee.
Yeah, or don't drink too much coffee because, well, at least in this part of the hemisphere, it's is the evening. Probably in Australia, if you are following us in Australia, it's just it's the sun is shining a lot, so you can you can take another cup of coffee.
Very, come on. Okay, then this is the result. Then you can see we have a lot of dry cell. This is because these cells are located around the highest value of the topography. Let me show you this phenomenon. I'm going to plot the topography. Topography. Acquire higher definition model tab. To change the color bar to gray, like this color bar. It's beautiful. And I'm going to plot the results using contour data. And we're going to see that the dry cells are located in this part where the topography has the highest values. Okay, and apply. Ignore this warning because our large river stage gradient around the rivers, but we can ignore this warning. We will close this. Then you can see the results, and we can see that the dry cells are located right here, and this part corresponds to the highest value of the topography. Then, okay, we have finished our simulation of this model, but I want to show you another model that we export from Geomodelr.
And
I'm going to show it to you, this model. This was created by one of our users. He's called Gilbert, and while this model is really interesting. This model is really interesting. Let me show it to you. It's called Umbita 1. Umbita 1, we can see here that this model is faulted, unlike the previous model, which did not have any faults. We can see here several presentations of our model, for example, a block diagram. A block diagram of our model. We will see in a few seconds our model again. You can also see the faults of this model. Let's see, for example, a block diagram with both that both covers a square. Let's see. Also, this model has. Let's put it at 0, and let's go to the top at. Let's check. Let's check at 3,500. Okay. And let's say submit. Okay. We will see here this this block we just created. Here it's processing rectangle. And meanwhile, we'll go creating a block rectangle with the poles and with cross sections, which are the input. Okay. It will take a few seconds to finish. And let's say submit. Okay. A few seconds to finish, and let's say submit. Okay. So it's ready, but the rectangle is not ready yet. But you can see here how the poles are starting to look when the rectangle is done. It will automatically load it here. Actually, it probably is done. Okay, you see, you saw that it automatically loaded it. Okay, let's see rect. Let's see this rectangle, which is what we are going to see in a few seconds in Model Muse. Okay, this is the rectangle, these are the poles, etc.
Okay, and let's see it combined with the different folds and the different cross sections. Okay, so this is what we're probably going to model on our next webinar. Right now, this model needs a bit of handling. We need to improve it a bit, but it looks really nice with its fault systems and with all its units. So it's going to be really nice to model it in 3 dimensions and to use it in Model Muse as an input. Okay, and but I'm going to show you how this model is exported here. Okay, so I'm going to select datasets. I'm going to select require hydrology. I'm going to select the hydraulic conductivity in the horizontal directory and say apply. Okay, close. Okay, and we can see here how our model, the model that Gilbert created, is exported to Modflow perfectly. Okay, so as I said, this model still needs a bit of work from the side of Geomodelr, but we can see that the export tool gets the solid model that is created in Geomodelr and makes it something really wonderful to work with. And so this is the end of our webinar. We learned how to create a conceptual hydrogeological model. We learned how to make it in Geomodelr using the tools it had. We learned also how to create the first cross section and how to create the cross sections from there until we have a solid model that we like, and that it also follows all the constraints we have, all the boreholes, all the structural data, all the information that we have as an input, of course. And after we finish doing this, then we'll have this 3D geological model that we can export to Modflow with hydraulic conductivities, with active or inactive cells, and with everything other information. And this model will be modeled in 3 dimensions. We can use Model Muse to apply boundary conditions or to make modifications to the model that we did. However, this model actually the most demanding task, which is to create the model in Model Muse or to create it in another hydrogeological platform, well, that demanding task is done. We finished it here. So thank you very much. I want to we're here to help you with your project. If you have any project that you want to share with us, if you have anything that you think it would be cool to see, it would be cool to model, we are here to help. We are part of the team of Geomodelr, and we are very eager to help you to model correctly and accurately and easily, so you can be more at the field and less in front of the computer. So thank you very much, and we hope to see you in our next webinar. Goodbye. Bye, everyone.